All right, let's talk about rotational inertia. So we know that torque, right, is equal to a force times a distance from a center of rotation. Now, we also know that force is equal to mass times acceleration. Well, we also know that linear acceleration, that tangential acceleration, right, is equal to your angular acceleration times the distance from the center of rotation. So using that, we can rederive our force equation to be that force is equal to the mass times the angular acceleration times the distance from that center of rotation. Now, let's go ahead and plug that into the torque equation. So torque is equal to mass times alpha times r times r, right? Or we get that torque is equal to the mass times the angular acceleration times the distance from the center of rotation squared. Now, the reason we want to get mass into the torque equation is because mass is going to make a difference in terms of the rotational inertia of an object, right? How likely the object is to resist initial rotations. Um, Now, it's not just going to depend on the mass, though. It's also going to depend on the distribution of the mass. And so what we call the moment of inertia, right, is equal to the sum of all of your particles within a structure times their distance from the center of rotation squared. Now again, this we call the moment of inertia, and this will dictate how resistant something is to um, your rotations. So for instance, if we look at the notes, we don't always have something that is uniformly distributed in terms of mass, right? Like for most of the torque questions, we were dealing with uh, a uniform meter stick, say, right? And that means that meter stick has the mass uniformly distributed throughout. So let's say instead we've got something that is shaped like this, where we can boil down the major mass points into three locations. Now, the moment of inertia, meaning how resistant it's going to be to rotating, is going to depend on these masses and how far away they are from the rotational axis. Now, typically, actually, no, not just typically, I'm going to throw it out there, you will not have to calculate your moment of inertia. This is going to be something that's given to you. But conceptually, you need to understand that the mass distribution on an object is going to determine the resistance to rotations. So for instance, let's say we've got two objects, and they're both going to be rolling down a hill. One of them is a solid sphere or solid disk, and the other one is a hoop. Now let's say that both of these have the same mass and they're the same size. So the center of rotation, right, is going to be directly in the middle. So we've got our disk here, and we've got our hoop. Again, these R's are going to be identical, and the masses of both are going to be identical. Well, if we put both of these on the same incline and let them go at the same time, one of these is going to make it to the bottom before the other. So pause the video, see if you can't figure out which one and why. Well, the one that makes it to the bottom first is going to have the lower moment of inertia, right? The lower moment of inertia it has, the less resistant it is to rotation, and so it will start to rotate at a quicker pace, and it will reach the bottom first. So the one that reaches first is going to be your disk. Well, why does your disk have a lower moment of inertia? Again, assuming these are the same size and have the same mass, Well, the disk has its mass distributed all throughout, right? You have some of the mass real close to the center of rotation, and you have some of the mass far away from the moment or the center of rotation. Whereas your hoop, all of the mass is located at a distance far away from your center of rotation, right? So again, if we look at this equation, the hoop has the majority of the mass far away, meaning that's going to have a large moment of inertia. So the disk will make it to the bottom of the ramp before the hoop. And again, conceptually speaking, the key thing to understand is that the moment of inertia is tied to that distribution of mass, right? The further away the mass is distributed from that axis of rotation, the greater the amount of moment of inertia, which means that the greater resistance to rotation. Now, the last thing we want to cover with the rotational motion is angular momentum. So think back to translational momentum, where momentum is equal to mass times velocity. Well, our angular momentum, L, is also going to depend on a velocity, right, omega, the angular velocity. But rather than mass, we're more concerned with that mass distribution. So your angular momentum depends on how is your mass distributed, right, the moment of inertia, and the angular velocity. Now, just like with translational momentum, right, translational momentum was conserved. Well, it's the same thing with angular momentum. However much angular momentum you start with, in the absence of some outside torque being involved, you have to end with that same amount of angular momentum. Um, so let's say, for instance, a good example of this is figure skating. And I'm also going to post a couple of videos on Google Classroom to kind of show you the demos that I did in class so that you can kind of see good real world demonstrations of the conservation of angular momentum. But a good example that you guys should have seen in TV at some point is figure skating. So let's say you got your figure skater, right, and they're starting their spin. And, it looks something like this. So they have these portions of their mass, right, at a far location from the rotational axis, which would be this. We'll call it P for the pivot. Now, what happens as they start to bring in that mass? Well, as they bring in their arms and tuck them to their chest, and they bring in that leg down here, well, your moment of inertia decreases, right? So you start with some amount of moment of inertia and some angular velocity. And again, as you bring these in towards your center of rotation, your moment of inertia is going to decrease. Well, if angular momentum is going to be conserved, what's got to happen? Well, their angular velocity needs to increase. Right, and so as that figure skater pulls their arms and their legs closer to their body, they begin to rotate at a quicker angular velocity. Right, and again, that's a classic example of the law of conservation of angular momentum. Now, typically, angular momentum and moment of inertia are really only covered conceptually. So, really, the key thing is understanding this relationship here between your moment of inertia and your angular velocity, and understanding that the moment of inertia depends on mass distribution compared to the location or relative to the location of their rotational axis. Now, again, I'm going to post a couple of videos of the same demos I did in class. I highly recommend you look at them because it's good to see this in person rather than crudely sketched stick figures. But this is it for the content for AP Physics 1. we will start doing reviews after this. I'll be posting up concept questions tomorrow and plan on testing early next week. I'll send out an email, also post on Google Classroom. Right now, I'm thinking it would be Tuesday and Wednesday of next week, so that'd be March 27, 20, or sorry, April 27, 28. Um, but yeah, I will see you all soon.